our theme today is the last transit of Venus that happened in 2012. That sounds like a long time ago, but knowing that the next transit will only be in 92 years and 360 days, I think we're still good talking about the last one. So the session will be double. So we have the first 45 minutes that we'll do now, and then there's a 10 minutes break, and we'll restart then at 15:30 CET for the next hour. So during the first part, we'll have an introduction by Paolo about the Venus Twilight Experiment, and then we will stream the Venus Twilight Experiment documentary film. A film, by the way, partly supported by Europlanet. After that, we will stream and listen to the piece by William Zeitler, which is called The Last Transit of Venus for Glass Armonica. It is composed and played by William and set to video by both William and myself. So here we will share the playbacks. So I will actually share it from my computer. So you can choose to listen here, or if you want to listen straight on your own computer or other device, there are two links in the chat. First link is the film, second link is the music, so you can watch them while we share here. Then we'll have a short break, as I say, and at 15:30 we'll be back. CET will be back here for the second hour, and we have two talks. One about a brand new science results with data collected during the transit of Venus, and the other one about Glass Armonica, Benjamin Franklin, and the transit of Venus of 1761. But more about that in the second hour. Let's go start with this hour. First, introduce to you Paolo Tanga. Paolo is a planetary scientist at the Observatory de la Côte d'Azur in Nice, in France. His research focuses on the minor bodies in the solar system. He is responsible for the data processing of solar system observations for the ESA Gaia mission, fantastic mission. And today he joins us as one of the initiative takers of the Venus Twilight Experiment that was conducted at the time of our last transit of Venus. And that was the first to investigate the aureola of Venus after more than a century during the previous transit of Venus in 2004. But Paolo will explain that better than I can. So Paolo, please, the floor is yours.
Thank you. I'm going to share my screen. So yes, it's a pleasure to be with you today. I'd just like to go now a few years back in the past, maybe even more than just a few, to explain you what do we mean for twilight phenomenon of Venus. What's the twilight for us is where we pass from night to day or day to night, the evening or morning. So the same happens on Venus, and some phenomena happens there at that moment. The first, if you go back really in time to the 19th century, we can find in some books and scientific papers this kind of drawings. These ones are taken from an account by Russell, observing in Sydney in 1874, and observing the transit at the time. And he saw that when Venus was crossing the limb of the sun, this strange bright arc was appearing. So he was not the first one to see this, but maybe the first one to draw it in detail with this bright spot and some variation in this arc along the limb. And he correctly suggested that this could be due to refraction in the atmosphere of Venus. So we are looking at the terminator. On the other side of the disk of Venus, it's the day, and the side turned toward the observer, toward us, is the night. So that's why we talk about twilight. We have the transition between the two, where we observe this kind of phenomenon. So what we talk about the aureole of Venus, aureola, but what is not aureola? We should also mention this, because when Venus gets close to the sun, but before or after a transit, for instance, when it is about 1 or 2 degrees of elongation from the sun, it can already appear as a bright ring like this. So this is a picture, a CCD picture I took myself with a small 18 centimeters telescope. In fact, it was the aperture reduced to even 5 centimeters. to avoid the sunlight to enter the tube. And the elongation was only 1.5 degrees. And you can see this entire ring of light, which in fact is due to diffusion, scattering in the atmosphere of Venus. So this is not what we're concerned now in the rest of the day, because this is a very faint with respect to what we talk when we mention the auroral, very close to the beginning of the end of the transit. So if just to look at a quick history of the transit of Venus in the modern era, starting from the first predictions of Kepler in the 17th century, we come to Halley in 1761. That's where Halley suggested that the solar parallax, so the distance scale of the solar system, could be established by measuring the timing of the entrance and exit of the transit of Venus on the solar disk from different Earth locations. At that time, it was the first time the auroral was already documented, the first time it was seen. In the 19th century, there was the first photographic observations. And then, of course, without any transit till 2004, it was no longer possible to investigate these phenomena. But in 2004, we had the first digital imaging that became available. And that's how a modern observer in 2004 saw the transit of Venus with techniques similar to those of Russell, so by drawing, and the auroral was there. But after more than 1 century, it was needed to confirm the historical observation to see if the auroral appeared always the same, how bright it was, how easy to detect, and so on. And nearly by chance, let's say I called for amateurs and professional astronomers that observe the transit to send images of the beginning and end of the transit. I collected images coming from several instruments, some amateur instruments too. So I don't go into the details here because I don't have time, but it was interesting to see that with those data, from observations that were simply meant to document a spectacular phenomenon without any possible implication for science, in fact, from those observations was really possible to do science, to measure the brightness profile along the limb of Venus, as it is shown by these brightness curves that span the portion of the limb that is outside the solar disk. So as Venus here exits the solar disk, the auroral becomes fainter and fainter, and at a certain point, we have to zoom to see this small increase in brightness that in fact correspond to the location of the south pole of Venus, because there the cloud deck is a lower altitude that allows more light to pass through. So it was possible to use a simple model implying refraction by a high altitude layer in the atmosphere of Venus, and to derive from that layer the scale height, the altitude itself, and then by using a simple atmospheric model, the standard atmospheric model of Venus at the time, the temperature. So it was quite interesting science that was possible to do by observing the auroral. And in 2004, nobody was still thinking to the possible application to exoplanets, or at least it was just starting as an idea. So in 2004, we learned that the auroral during the exit and entrance on the disk of the sun can vary by large factor in brightness, 2 orders of magnitude. That can allow us to determine physical parameters of the atmosphere, variation in latitude, all at instantaneously or at several large latitude range, a typical brightness of about magnitude minus 6 per linear arc second, about 100 times fainter than one square arc second of the photosphere, but still visible, well visible with solar filters even by the naked eye. So then the idea was, a few years later, in 2012, to take the opportunity of what we learned in 2004 and to build a specific instrument to try to optimize the signal to noise, the signal coming from the auroral by hiding the photosphere of the sun with the coronavirus. So we involved in the project Alain and Sylvain Landy, 2 opticians in Toulouse, that amateur observers that built and optimized several coronagraphs. And this is one of their images obtained in 2004, showing the bright arc of Venus here, outside the limb of the sun. And the idea was to modify this instrument in such a way that we had a correct image scale. We were not interested to see the whole sun, but only a portion of the solar limb close to Venus. And to do this, it was necessary to decenter the occulting disk of the coronagraph to be able to put at the center of the field of view the limb of the sun and not the center of its disk. So all these modifications were proven to work, and we decided to deploy several of these instruments based on small 11 centimeter aperture refractors in several places where the aurora was visible. And so we were able to collect measurements of it. And this was an example of images, a sequence of images obtained by my coronagraph that was, which I was in charge at Lowell Observatory, where the transit was well visible in the morning. So you can see here these different times of the Venus ingress, first with the polar spot and then with the aurora increasing in extension, in latitude, and in brightness. So that's the essence of what we did. More, you will see more later. Pedro and Alexandre will show more applications of this, also because the Venus Twilight Experiment was just, I can say, a way to put a special attention on this twilight phenomena and motivate many people with even with large instruments to collect very useful data. And we will talk about that along this seminar. So thank you very much. I stop here and leave the floor to the next presentation.
Thank you so much, Paolo, for giving the background context here. I think now we will go straight into the film, and that will show the whole how we actually did it. So the documentary will show the human side of the whole experiment. Actually, it was filmed over a several years period in around 2012. And the music is also composed by William, who is here, and performed by himself on the keyboard and the Glass Armonica, and by Ilse de Zay on cello, and by Dori Mead on voice. So let's go to the second part of our session today. We have two talks. The first talk will be by Pedro Machado and Alexandre Branco about some very, very fresh results indeed concerning the transit of Venus and making the connection to the exoplanets. And then the second talk will be by William Zeitler about some history here and about the strange instruments he has you have seen appearing on the screen, and these magic sounds and everything that is behind that. Let me just introduce you to our speakers. So Pedro Machado is a planetary scientist, and he works at the Institute for Astrophysics and Space Sciences in Portugal, and is professor at the Department of Physics of the Faculty of Sciences of the University of Lisbon. The focus of Pedro's research work is atmospheric dynamics and atmospheric composition of the planets of our solar system. For the dynamic study, he developed a method using the Doppler effect in combination with high-resolution spectroscopy. He is an invited scientist for the Japanese Akatsuki mission to Venus. He is part of the Venus Express mission science team. Well, was, because the mission has finished. He's also a co-PI on a future mission, the ESA Ariel mission that will look at exoplanets' atmospheres, and a co-PI on VenSpec, an instrument to fly to Venus on the new ESA Envision mission. He's also co-PI on the Omega instrument on Mars Express that is still orbiting Mars. Alexandre Branco is finishing his master's degree in astrophysics at the Faculty of Sciences at the University of Lisbon. And he also works at the same Institute for Astrophysics and Space Sciences in Portugal. His dissertation focuses on the characterization of the atmosphere of Venus and of the ultra-hot Jupiter-like exoplanet with the fancy name WASP-76b. And he uses high-resolution transmission spectroscopy to do these studies. He's interested in studying the diversity of planetary atmospheres that can emerge across our galaxy, ultimately trying to figure out the frequency of habitable worlds and the conditions which can make them conducive to life. Our second talk will be by William Zeitler, and William is a musician, as you have seen. He is also a composer. He's a professional pianist, organist, and harpsichordist. He's also one of the very few people, I don't think there are more than 10 on our planet today, who play the Glass Armonica, and you have seen him play in the last video, and about which we will hear a lot more. William is also the author of the one and only history of the Glass Harmonica, a book entitled The Glass Harmonica, The Music and the Madness. So this could be a good read for the Christmas time. As a composer, he composed and recorded 10 albums, composed music for film, as you have seen, and more recently he's also composing music for computer games. So you might be buying a computer game and it has William's music on it. In addition to all that, he's a programmer, software engineer, taught mathematics at the Monterey Peninsula College for several years. And he's generally very interested and knowledgeable about science, and in his own words, in an amateur capacity, of course. So let's go to the first talk. First by Pedro and Alexandre. You have the floor.
Thank you so much. We're just sharing our slides. Hope everyone can see them.
They're just loading for us. There we go. We see them. We don't see them in presentation mode yet.
Do you see them now in presentation mode?
Looks good.
Yes, that looks great.
Perfect. Okay.
Okay, so I will start from here. Thank you, Martin, for your words. And so what I will start to share with you is, in fact, a legacy from the beautiful film we saw from this amazing Twilight Experiment, this project that was a dream made true by Paolo Tanga and Thomas Widman and many others, as you could see before. And so but there is a legacy, a historical legacy that will, the last step was a couple of days ago with new results that we will be sharing with you now. So here you can see the aureole that was already told about and on the previous film and on the words of Paolo Tanga. And of course, here we can see the arc and the study of the arc by Lomonosov. And after, so that came the interest to going to places where we could, in fact, see the aureole along a Venus transit. So with that, we go back centuries ago, for instance, for the expedition of James Cook to the Tahiti to observe the transit of Venus in the old times. And after this expedition to Kobe by Jensen in Japan. And finally, as you already saw, so Martin and Paolo, I think that we are all here, at least the people that are here from the Venus department, let's say, and Thomas Eden at the Paris Observatory. And well, now let's depart. And this we depart with a cake because we are around Christmas time. So our colleagues in the Lisbon Observatory, they made a cake with our it's me and João Retré drawn in the cake, as you can see, in the day of the departure to Udaipur and to perform these photometric studies with the siderograph, as Paolo Tanga well explained before, in the framework of the Venus Twilight Experiment. So here you already saw about our friend elephant and all the adventures that we lived there. But the thing here that I want to connect with the results that Alexandre will, in a while, will share with you is, well, how we can see today when we hear in the news where it was detected a new Earth-like exoplanet. It's an Earth-like or a Venus-like exoplanet. So, and we intended with this project that we used the data that was collected in the same day of the last transit in June of 2012. So, and the idea was with the satellographs to use these data with a downgrading capabilities of our observations. So looking to Venus as it was an exoplanet. And there are several things that are really important here. So how we can disentangle these two cases. So often we say that Venus is a kind of evil twin to Earth. So it's a still lovely planet like Earth, or is a kind of incinerator like Venus, even if I still like very much Venus. So we must look also to the spectra. So the main take-home image message that I want to share with you is that we must also look to the spectra. So there was a twofold observations during the last transit of Venus. The photometric, as you saw in the movie and in the words of Paolo Tanga, but at the same time, there were some unique data, high-resolution spectra, taken at the same time as we were scattered in the world, collecting the images from the aureole with the satellographs, but at the same time were collected extremely high spectral resolution. And with that, because these spectra were collected by transmission spectroscopy, so that is a technique that is often used for characterize exoplanets' atmospheres. And the thing is, the same observables that we can retrieve from the transmission spectra collected during the transit of Venus, we can also study them with other probes like Venus Express, as we saw in the movie, or from ground-based observations. So this unique data is important to give us a template to calibrate the transmission spectra for exoplanets. And at the same time, to see if a planet has a nitrogen-rich atmosphere or a CO2, so carbon dioxide-rich atmosphere. And so that was the purpose of the project that ended a few days ago. So the results were published a couple of days ago. And for that, I will leave the floor to Alexandre that will go sharing with you the details about all of this project. Thank you. Alexandre.
Thank you so much, Pedro. And so this brings me to what we have been doing with this transmission spectroscopy study of the 2012 solar transit of Venus. So Venus transited in front of the sun, as everybody here knows by now, and we could spot its atmosphere in this shining arc of light, which comprises starlight that has filtered through the atmosphere of Venus. And that ends up with all the fingerprints of the chemical compounds that make up that same atmosphere. So this is just the atmosphere that is closer to us, so the one of Venus. But could there be multiple Venus-like atmospheres out there beyond our solar system? So we are pretty much familiar with this concept of habitable zone, where planets would, in principle, support liquid water in their surface, and therefore we could expect an Earth-like atmosphere to emerge. But there is also this Venus zone, where a Venus-like atmosphere might instead emerge. And that area around a star, independent of the stellar type, is where most of the candidates which we are now planning to start observing with space observatories such as JWST fall into place. So it's quite interesting to see, using Venus, what are the observables that we will recently find, we are about to find in those same atmospheres out there, and that is the Venus zone. So how can we exactly detect these planets and study their atmosphere? So just like Venus, some of them pass or cross in front of the stellar disks of their host stars. And we can monitor the flux of those stars and maybe infer that their luminosity will decrease, or the flux that reaches will decrease temporarily and periodically. And therefore, we can infer the presence of the planet there and use part of the starlight that still reaches us when that planet is in front to infer the composition of the atmosphere. So one of interesting case is the TRAPPIST-1 system, which is made up of 7 exoplanets until now, some of them the size of Venus and Earth, so Earth-sized exoplanets, and some of them are already being targeted by JWST, and it's a question of whether or not they even have an atmosphere, and if those atmospheres could be Venus-like or Earth-like. So to do so, we use transmission spectroscopy, and there are several observables throughout the spectrum which we can look at. For instance, in the optical, we are more sensitive to atomic absorption, so absorption from atomic species in the atmosphere, and also to scattering due to the presence of hazes or clouds. And as we move into the infrared, so longer wavelengths, we start being more sensitive to molecular absorption. So the closest region of the infrared to the optic is the near infrared, and that is exactly where our study looked in the spectra. So we did transmission spectroscopy of Venus in the near infrared. And for that, we used observations from the Dune Solar Telescope performed with the instrument FIRS, so the Facility Infrared Spectropolarimeter, which is a high-resolution spectrograph with a spectral resolving power of 90,000. And those observations were comprised, so the wavelength that was probed was between 15,624 and 15,680, so in the near infrared. That's where we took a look at Venus' atmosphere. So to extract these transmission spectrum, which ultimately would give us the desired information, we took a look at several exposures throughout the moment where Venus was crossing onto the solar limb. So at the moment where part of the disk of Venus was superimposed into the solar disk, and other side was not. And at the side that is not in front of the sun, we can in fact see over here at the top, between these two vertical dashed lines, the region of the aureole. And that's where we focused, and from those were the pixels essentially which we were interested in to extract our transmission spectrum of Venus. So this is just a kind of a zoom into that region where we kind of aligned all the pixels by their maximum intensity. So we could then select a short window around this aureole region, which is marked by these two horizontal gray lines, red dashed lines, which is the Venus limb, where light is in fact being transmitted through the atmosphere. It is bent as it interacts with the atmosphere. And so this is where was our region of interest, but we also had to select this background region so that we could kind of correct for any unwanted light that was contaminating our spectrum. So we could, after making all of these calibrations and corrections, we could combine all of the information contained in each of these spectral pixel and retrieve the transmission spectrum, which we show here in gray. So there are several features we could readily identify that pertain to carbon dioxide, which is the major component of the atmosphere of Venus. And we could, in fact, disentangle between two isotope plugs, so two different molecules of carbon dioxide. So the carbon-12, so a molecule with carbon-12 in it, and another with carbon-13. And there were plenty of features from these molecules, isotopologues, which would only be observable in high resolution with these observations we were analyzing. However, we could also trace signals from carbon monoxide, which is another constituent of the atmosphere of Venus that results from the photodissociation of CO2 as it interacts with the solar radiation. And here we mark all of these spectral features we could spot, and as well as these three forward models we made for the transmission of these species in the atmosphere of Venus, so that we could take another look at the spectrum, or another analysis technique into the spectrum, as I will now explain. So we were indeed interested at looking at Venus as an exoplanet. And typically we don't have as much signal for exoplanet atmospheres as we do here for Venus. And what this implies is that there has to be a way for us to disentangle the small signs of atmospheric transmission in high noise spectra that is collected for exoplanet observations. So here we could really calibrate this technique, that is the cross-correlation technique, which takes advantage of the transmission models I just showed and kind of correlates that with the data that was retrieved observationally. So when there is a great match between our models and the spectral features in the spectra, we see that there is kind of a peak in this cross-correlation function, which is in practice just an average throughout the wavelengths that we are selecting with our template as we slide it across the spectrum, so that we kind of we probe all the different wavelengths. So this is the results we got for applying this technique in the transmission spectrum from the Venus Oriole retrieved during the 2012 transit. So you could clearly identify cross-correlation peaks for the two isotope lugs of carbon dioxide and also carbon monoxide, which we had already seen in the spectra, so kind of more straightforward. So we were kind of expecting to see them here, and it's great because it kind of proves that our models are sensitive enough and our line list, so the position where each absorption line is expected to take place, is kind of well defined for us to make these detections with this technique, and in principle would also work with exoplanet observations. So we made these three detections with significances of 4.2, 4.7, and 3.9 sigma. So we are also motivated by this very interesting result from 2011 that made the first detection of an ozone layer on Venus. So this is a result from Montmensin et al. In 2011, and it shows here in these two graphs the various positive detections of ozone on Venus throughout different altitudes, which in fact overlap with the altitude to which we were sensitive with the transmission spectroscopy technique during the Venus transit. So we were interested in seeing whether we could also use the cross-correlation technique to detect these Venus ozone layer. And in fact, we got a tentative signal of ozone on Venus, which is quite fascinating. It's slightly less a slightly weaker signal than those of carbon dioxide and carbon monoxide, with a significance of only 3.5 sigma. But the suggestion that these molecules could in fact be detected on Venus with transmission spectroscopy and the cross-correlation technique might indicate or might support this idea that the presence of ozone on an Earth or an Earth-sized planet atmosphere might not just be a hint towards habitability as it is on Earth. So our ozone layer is greatly dependent on the development of or evolution of photosynthesis due to the Earth's biosphere. But what if there is also ozone out there that it doesn't really rely on the presence of a biosphere and could result in false positive on biosignature detections? So ozone on Venus relies on this balance between its formation via the photodissociation of CO2 and its destruction via reactions with subproducts of photolysis of water. So in principle, if we have a quite desiccated atmosphere with no water, there will be no components that would destroy O3, and therefore it could accumulate and suggest that we might in fact be looking at a desiccated atmosphere like Venus. So it's quite an interesting probe, even though our detection is quite tentative as well. So this takes us into the future directions of the study, which is actually looking at Venus-like planets or at Earth-sized planets, which might have Venus-like atmosphere. And those instruments will, such as the ELT, the Extremely Large Telescope, would allow us to do that. And it's about to see its first light in 2028, 2029. And there will be instruments with high resolution in both the optical and the infrared, which would allow us to look at atmospheres of Earth-sized planets outside of the solar system, but also the Ariel space mission, which will look at 1,000 atmospheres of exoplanets and try to characterize them and study the chemical composition that is the makeup of their atmosphere as well. So it's kind of interesting to take a look at our analysis and see what we can expect as we will start to analyze the data from these observatories, but also the Venus itself. So the study of Venus doesn't end, it's far from ending. And there will be missions such as the Envision mission from ESA, which will take a look at its atmosphere as well. So it's quite interesting to see, for instance, the isotopic ratios we could measure with our transmission spectra, since we have already detected these isotopes, and compare them with future measurements from the Envision spacecraft. That would be really interesting to see. But until that is possible, you can take a look at our paper that is now publicly available to everyone. And thank you so much for the opportunity of giving this talk and for listening to me. And we would be happy to take questions.
Thank you. Thank you so much, Alexandre. Thank you so much, Pedro, for this very nice talk, and congratulations on your paper and these very interesting results. Okay, we'll do the Q&A after we hear from William. So, William, would you like to share with us your thoughts and your insights?
All right, so I was playing the Glass Armonica. You saw me on the video.
William, I think you have to put your microphone.
Oh,
yes.
Thank you.
Yes, that's better. Okay, great.
There we
Thanks.
go. Right, so I was playing this instrument called the Glass Armonica, which was invented by Benjamin Franklin in 1761. So that's a fun coincidence with the transit. And so Franklin, amongst his many interests, was also very interested in music. He was a capable amateur musician himself, played a half a dozen instruments well enough to amuse himself or amuse his friends at parties and such. And he attended a concert by a colleague of his in the Royal Academy who was performing on a set of water-tuned wine glasses, like we've all done at Thanksgiving time with the wet finger around the wine glass. And Franklin was enchanted with the sound and decided to come up with a more convenient arrangement of the glasses. So first of all, he wanted to do away with the water tuning because it's always evaporating and going out of tune, and every time you want to play, you have to tune it. And also, he wanted to be able to play more than two glasses at one time. And he wanted to be able to have a lot more glasses available to play. So his idea was to take the glasses, he had them hand blown, but the idea is to turn the wine glass sideways. It had a hole and a cork in it, so each glass was mounted on its own cork, and the glasses were turning instead of having your finger go round and round. And because they were nested inside of each other like the bowls, cereal bowls in the cupboard, the rims were close together so you could play it somewhat piano-like. So it became very popular in Europe especially. Even Mozart and Beethoven composed music for it. But around the turn of the century, the world of music was changing and was moving out of their aristocratic halls. The aristocracy was kind of going away between the French Revolution and Napoleon put an end to the Holy Roman Empire and all of that. So musicians found themselves turning to public performances to feed themselves. And the larger the hall, the more tickets you can sell. And so instruments in general were re-engineered to be as loud as possible. The string tension on the violin was increased. They took all those Stradivariuses apart and reinforced them. And brass and woodwinds are also re-engineered to be louder. And the piano also, it started out like in Mozart's day, string tension was around 25 pounds or so per string, versus the modern grand piano is more like 200 pounds. You have more kinetic energy, so you just get more volume out of the instrument. But there was nothing they could do to make the glass harmonica louder. So we have accounts from the period of reviewers saying, gee, the glass harmonica was really lovely if we could just hear it. And so it didn't take very long before it was abandoned altogether, and it's now on the endangered musical instrument list. So that's the basic story on the glass harmonica. But in the course of researching my book, I came across a story about how science was done in the late 1700s. That was my favorite story in the whole writing of the book process, which I thought I'd share with you, and it kind of ties in with Franklin and all of that. So if we back up just a little bit, at around Franklin's book on electricity came out, and so he published it in 1751. And Franklin was the first to propose what is essentially our modern theory of electricity. At the time, the thinking was that maybe it's two fluids, one that has an attractive property and another that has a repulsive property. And another theory that was common at the time was that it must be some sort of mystical new kind of material altogether. And Franklin was the first to propose that no, it must be some sort of a fluid that flows from pole to pole. And let's call those positive and negative. And in his book, he outlined a series of experiments that demonstrated this. Like one of them, for instance, was connecting two Leyden jars in parallel. A Leyden jar is an early capacitor. And he was able to show that the charges would even out between the two Leyden jars, suggesting that it had sort of fluidic properties. Now, Franklin didn't have any math background to speak of. He only had a second grade formal education. And so he didn't put any math around it. That was left to others. But his series of experiments, laid the foundation for, and it was the big breakthrough for our modern understanding of electricity. Now, the thing is, in those days, America was just a bumpkin nowhere on the forgotten edges of the world. And the idea that some tradesman with no university, much less even high school education, could solve one of the major problems of the day would be like today a tradesman in Somalia solving or proposing a breakthrough in dark matter. Like the scientists in Europe that, this can't possibly have any validity to it. And so it was kind of an uphill battle. There was Father Beccaria at the University of Turin who read Franklin's book, realized that Franklin was really onto something, repeated all of the experiments that Franklin itemized in his book, and was able to really champion Franklin's ideas on electricity in Europe. So the story I've got is about just that. So I'm quoting from my book, and first I'm setting up what is an eyewitness account. So here's the background, and then I'll do the eyewitness of account. So meanwhile, an invention of Franklin's that put his electrical insights to practical use, the lightning rod, wasn't. By the way, in Franklin's book, he also introduced the idea of the lightning rod. Wasn't immediately embraced with open arms either. One group, this is in a city in Italy. So largely the situation was that the old school scientists were very dismissive of these ideas. They can't possibly be true. Where the younger generation was, wait a minute, these might have merit. So one group that opposed was essentially religious. Lightning rods were thwarting God's will. Holy water and the ringing of church bells were the only unsacrilegious defense against lightning. The other group objected on a more scientific basis. The Marquis Shigi, for example, maintained that electricity does not exist in the natural state, that lightning is not at all an electrical phenomenon, that pointed conductors can in no way keep lightning from forming, and that they are of no use in receiving and dispersing strokes. Matters came to a head in 1777 when the Grand Duke ordered lightning rods to be placed on the cathedral and the Gothic tower of the City Hall in Siena. Hot controversy divided the citizens of the little medieval city, with the Marquis Shigi on the one side and the university professors on the other. Once the rod was up, according to a contemporary report, one can say that never was a wedding day awaited with so much anxiety as was a storm by the two parties. There wanted a lightning storm to happen. Fortunately, they did not have to wait long. A colleague at the University of Siena describes the spectacular event, and here it is. This is my favorite story. It will not be easy to find a similar observation attested in all its circumstances by a large number of people who, in a thickly frequented public square, in plain daylight, and with all their attention, had their eyes turned toward an extremely high tower to observe the action of the conductor recently placed upon it, and who, without a long wait, had the fortune to admire, to the glory of philosophy, the intelligence and the genius of the immortal Mr. Franklin, who, extending, so to speak, his prodigious hand over the square of Siena on the 18th of April, took by the hair a horrible lightning bolt and forced it to pass along a route mapped out by his great mind, with express orders not to damage a building on which it had so many times vented its furious strength. The people of Siena, always grateful to one who does good to humanity, are surprised that statues have so often been raised to those who have ruined cities, and that they are so seldom raised to those who preserve them. If Mr. Franklin reads the present account, he will surely feel an ineffable consolation. So there you have it. That was kind of what science felt like in the late 1700s when the 1761 transit occurred. I hope you enjoyed that story as much as I.
Well, I have been smiling and laughing.
Isn't that great?
And enjoying it very much. Yes, thank you so much for that great insight and sharing that with us. Yeah, it's amazing.
Franklin also championed, he encouraged astronomers in the colonies to observe the transit. He appreciated the importance of it, and he tried to observe it in London, but of course it was foggy that day, so he wasn't able to see it himself.
That sounds like when they tried to go back to possibly see Neptune. So the whole discovery of Neptune, that's a whole other webinar we should do. But there's the account talking about London and the bad weather. So in Cambridge, they think they saw something.
Right.
Okay. Then they went for tea, of course, because they had to have tea. and then let's double check. Oh yeah, but then the clouds had rolled over. So yeah, no. So then they didn't check, and they missed the discovery. It was a whole incident. But okay, that's another webinar. Thank you so much. Sorry, thank you so much, William. Thank you so much, Pedro, Alexandre. Thank you so much, Paolo, for your great interventions, for your great talks. Thank you all the attendees for being here. Yeah, so I think we have some time for questions, interaction. If you want to ask your question, typing in the chat, that's fine, or in the Q&A. Or if you want to speak, we can unmute you. We can allow you to speak. So anybody.
Can I start us off while we wait for
absolutely.
in the Q&A?
Please.
William, my question is not scientific in nature, but actually just around the glass harmonica, with the technology that we have now, and we're no longer constrained by having to have our instruments as loud as possible to fill an enormous European music hall. How does the glass harmonica compare now in a live setting? Is it easy to mic up? Is it something that you've tried? Is it something you've looked at? It's my first time encountering the instrument. I'm really fascinated by it, and I wonder how it can be converted into a live experience in 2024.
Right. And one of the things I find fascinating about it is that most, or maybe most instances of genius are such that you require a lot of background to really appreciate it, where the idea of going from this to the Glass Armonica is like, wow, what a stroke of insight, but anybody can understand what the problem was and then appreciate the solution. So sure, of course, in fact, I don't ever play without amplification anymore, just mic it in the normal way. So, amplification was invented early in the 20th century, so it was nowhere near available in the night, of course. But even in spite of that, it doesn't seem to have helped the Glass Harmonica get off of the endangered musical instrument list. So it's kind of curious that way.
Yeah, interesting. Thank you.
You're welcome.
I think, William, the last time you played systematically was a big orchestra in Toronto with a piece that had the glass harmonica in there, right?
Yeah, there's an opera, Lucia di Lammermoor, Donizetti, that has a substantial glass harmonica part. So the rough plot in the opera is that Lucia slowly goes mad and goes all the way off the deep end in the third act and has this extensive duet with the glass harmonica. So, and we amplified it for that. In fact, I don't see how it would be possible to do it without amplification and be heard. So.
Surely.
I mean, it's as loud as the wet finger. You've all done that, so that's how loud it is. It's not loud at all. And to pit that against an entire orchestra, or the prima donna of the opera has a huge voice, and here's this feeble little glass harmonica. I don't know what he was thinking. Apparently, they had personnel problems with the glass harmonica player in the original performance, so he wrote parts for flute to play the harmonica part, and that's how it's frequently done now still.
Okay.
But with the glass harmonica, his original idea was really cool. It really works.
I bet. How did you come by your actual instrument? Is it something that can be bought commercially, or is it something you have to get custom made?
There's a maker in Boston, and then there's Sascha Reckert in Germany who makes harmonicas also. I don't know if he still does, but he did at one time. So there's a couple makers in the world.
We must make sure to have one for the 2117 and 2125 transits.
Absolutely.
Mm-hmm.
We'll be making them out of I don't know what.
Glass made out of stuff from asteroids or something. I don't know.
Yes, right.
Asteroid mining.
From the fourth dimension or something.
Something like
Quantum harmonicas. There we go.
Quantum harmonicas. There we go. Any other questions? I actually have a question. If there's no other questions now online, or anyone wants to speak about ozone on Venus. So that's really very interesting. I think 3.5 sigma is still pretty good. I mean, maybe not as good as the other ones you had in the other detection, but still, Anyway, so how would you move forward from now? Because you needed the transit to see this, right? Is there any other way we could do this and detect before the next transit in 2117, or before we go there with spacecraft in the 2030s?
But possible. So I will. What we are thinking is that the dream must go on, and so we are preparing new steps. One is about measuring. So Alexandre will be doing that together, and perhaps with a colleague that now is in Brussels, about measuring the isotopic ratios, which will be a great result if we can do it. So let's see if we are lucky again. And the other thing is what you showed in your movie about the Twilight Experiment. So comparing with the SWAR instrument on board Venus Express. So the idea is to compare the results and again try to build up a better and robust template about transmission spectroscopy. And finally, we have an idea with this nice gentleman that is with us today, Paolo Tanga, for using the same idea of transmission spectroscopy, but not waiting for the next transit of Venus, because even if we go to the gym every day, that will be a bit difficult to 2117. So our idea is perhaps to look for a bright star passing behind one of the ice giants and to retrieve the transmission spectra on this. So that will be again a synergy between Ariel space mission endeavor and our work. So Paolo, we are counting on you. So the next chapter of this dream will move forward. So, but we will need you for sure. So thank you.
Well, if I can add just an element here, what we observe in the transit of Venus, in fact, is the refraction from a layer of the atmosphere when Venus is crossing the limb of the sun. But when you have an exoplanetary transit, you are in fact implicitly observing the same thing, because the light passing through the atmosphere is refracted in that case too, even if the planet is completely superposed to the sun. So to have a correct interpretation of the spectral signatures you see, we have to take into account that the light is refracted, not only absorbed. There is clearly a deviation, and this deviation affects the layer we are observing, the intensity of the spectral bands, and it has already been modeled now in some transit models of the atmospheric absorption. But let's say before the transit of Venus in 2004, it was a neglected effort.
Because what we're seeing, what you also detected in your work, it's quite high in the atmosphere. We're talking, what is it, 100 kilometers? What's
Yes, it's very high.
Yeah, exactly, right.
Yeah. It's up in the upper layers of the atmosphere. Above 90 kilometers, so between 90 kilometers and 100 kilometers.
Yeah, that's also because Venus is covered by a thick clouded deck, which is very, very reflective and absorbing. So you certainly have to go up above that to see this effect.
Okay, I think we have a question from Walter Reis for Paolo. I have what can be called a stupid question. No, stupid questions don't exist. But are the coronagraphs still usable? And can't they be used by amateur astronomers to observe sun-grazing comets like SOHO and Solar Dynamics Observatory do? Is it possible, do you think?
Well, it's an interesting question, but the coronagraphs were built to have a kind of higher resolution of the auroral, so a field of view of a few arc minutes. So it's very difficult to use them to observe any other object, because you just see a portion of the solar limb and a very small field of view.
Does that answer your question?
In addition to that, to mention that anyway, the auroral is visible in a wide spectral band in which you cannot easily suppress the background. So you have diffuse light anyway. And so to see anything faint is impossible. Unfortunately.
Unfortunately, yeah. Fully explained, says Walter. Okay. Excellent. Any more questions? No. William, so we have been working together for 14 years now or something like that.
Yeah,
more,
at least
16?
something like that.
We actually met through the Glass Armonica in a way, because my first video, I needed some classy sound of music and you had that. But so how do you, when you compose, how do you, what is your process? How do you get to the melodies or to the harmonies? How do you, what's going on in your brain, so to say, if I may?
Oh no, scary.
Oh dear.
Right. Well, so the process that mean, everyone's different, but for me, what has ended up working is first I'll just kind of noodle around on a keyboard. I'll look at the film if I'm doing a score and like, okay, what's the feeling here? What's the tempo? Like, is it up tempo or slow, contemplative or whatever? And then I'll just noodle around on a keyboard with the recorder running, and inevitably I'll get the germ of some musical ideas. And then I kind of switch into more analytic mode with my editing. I've got the formal training and all the rest of that, and take those ideas and then kind of nail them down into a more coherent, polished form.
Okay, thank you for.
So switch from right brain to left brain, kind of. Start with right brain, go to left brain. And I guess that's not that different from science, too. A lot of great insights have come from dreams and, very bizarre things. And then the analytic side kicks in and takes that idea and runs with it and turns it into something like Einstein is, what would it be like to ride on a beam of light? What would the world look like? And that starting with that fantasy, and then starting to put analysis around it.
Yeah, I guess so. And even, way of doing science. Okay, I have some data. Let's just try something. We'll just average something or see what happens. Just
noodle around. Yes,
noodle around. Right. I guess that's at least my process. I don't know about anybody else here, scientist on the connected to us. I think it's pretty much how I do. So, okay. Any other questions or comments? You've been with us for almost 2 hours now.
Or so just a curiosity again on Glass Armonica, because this is the domain I know the less. Has anybody tried to build a Glass Armonica with other materials than glass? I don't know if you mentioned that, but in metal or?
Right. Well, okay, so there are like the Tibetan singing bowls, where you make them sing with the wooden dowel rubbing around it. That's exactly the same principle. Okay. But so it all depends on, in essence, it's a glass, in the case of the Glass Armonica, it's a bell. It's a glass bell. And so some materials are prone to vibrate. Metal ones would work fine also. And others, like plastic, not so much. So yeah, the material matters, but you could use different kinds of glass or other kinds of material. In the case of glass, there's a whole families of different kinds of glass. There's soda lime and borosilicate and so forth. And those all have different like coefficients of elasticity and whatnot that give each of them a different little subtle color, like the difference between, say, a bronze versus an aluminum bell, I guessed. So there's a lot of nuance to it when you get into it. It's surprising. And interestingly, bells are one of those, the vibration of bells is something that's only been solved. You can only attack it with numerical approaches. There's no closed form solution for bells yet. Maybe never, I don't know. But at any rate, yeah, they're really complex things.
Interesting, thank you.
You're welcome.
Thanks for your questions, everybody. Are we happy to close off, Martin, if everybody seems happy with the...
I think so.
There we are.
I think we had a very, very nice end of the year session. Yeah, I think if there's no more questions or comments, then we will call it a day or an afternoon or a morning. And thank you so much again for being here with us. Thanks for all the people attending, and we will see you next year. Thank you so much. Have a great end of the year season for everybody.
Thank you.
Thank you.
Okay.
Bye-bye.
Bye, everybody.
Bye-bye.